All right, thank you very much. Today I'm going to talk about AS Ultra, which is a new product. It's an advanced amended silicate for mercury control. Here's an outline of what I intend to cover today. First of all, I'd like to talk about how our product differs. It's a powder product that's injected into the duct at power plants like activated carbon. I want to talk about how it's different than activated carbon, and specifically talk about how historically in the past it's performed differently than activated carbon in spray dryer baghouses and circulating dry scrubbers, as well as how it performs relative to plants configured with a Cold-Side ESP. And I'd like to talk about reactive capture versus absorption. I'm going to talk about some of the added benefits besides capturing mercury that amended silicates has. Talk about the historical success of amended silicates at capturing mercury and where we intended to go and how we got to our new product. The laboratory testing that we did in order to evaluate new formulations, and then the full-scale demonstration of our new product, both at plants that are configured with a Cold-Side ESP only, and plants that also have a wet FGD. All right, so to start out then, activated carbon captures mercury by absorbing mercury and desorbing mercury, continually adsorbing mercury and desorbing mercury. It has to have the mercury oxidized to capture any appreciable amount of it. And so there is a chemisorption reaction, particularly even if you're just absorbing the chlorine onto the carbon in the flue gas, or certainly if you have a brominated carbon, for example. That's a chemisorption reaction, but once that oxidation happens, excuse me, get some water with me. Once that oxidation happens, then the oxidized form of mercury is absorbed to the carbon, and so it desorbs and reabsorbs and desorbs and reabsorbs. And so looking at the reaction rate or the capture rate of mercury from the flue gas for activated carbon, the change in the concentration of mercury in the flue gas with respect to time, that's a function of both an absorption term and a desorption term. And the desorption rate is a function of the amount of mercury absorbed on the activated carbon. So initially, the mercury capture rate when you inject that carbon into the flue gas is very high because you don't have any mercury on the carbon, so your desorption term is 0. Your adsorption term is as high as it can be, and you have a high rate. Over time, as you obtain more carbon utilization, the desorption term grows, and your rate declines and eventually stops. The disadvantage for activated carbon is that it's limited to low sorbent utilizations. Now, in standalone Cold-Side ESPs, activated carbon performs very well relative to other products because there's not much residence time for it to capture mercury anyway. So any product's going to have a sorbent product utilization issue because there's not much time for the reaction to take place. And since there's not going to be much utilization, that for pretty much most plants, that carbon stays pretty active, the desorption term doesn't grow, and you get pretty fast reaction. You get better performance than other powders. It has not done comparatively as well in spray dryer absorbers with longer residence times and circulating dry scrubbers. Yes, you get much higher sorbent carbon utilization in those plants, so relative to itself it does better, but as it increases the utilization, that desorption term increases, reaction slows down, and stops. So another product can do better that if it's not limited to, doesn't have a desorption term. All right, now amended silicates. How is amended silicates different? Amended silicates reactively captures both oxidized and elemental mercury. It basically follows a first-order reaction. It doesn't have any desorption. And the advantage is that you can have high sorbent utilizations. Another advantage, actually, for this product is that there's no halogens needed in the product or out of the product. No halogen addition means that there's no added halogens to the scrubber or the ponds. There's no corrosion potential. In the longer residence times associated with spray dryer absorbers and circulating dry scrubbers systems, which have allowed for the high utilizations of this product, amended silicates have performed very well and outperformed activated carbons. In the short residence times of cold-side ESPs, amended silicates have had difficulty in the past because of their low mercury capture rate. However, the new products that I'm talking about today have a higher capture rate, and these have solved that problem. Now, this is really to give you an understanding of what I'm talking about. I'm going to mention the word performance improvement or relative rate. And this is what I'm talking about. I'm describing that here. As I mentioned, the capture can be described by a first-order reaction. Change in the concentration of mercury in the flue gas with respect to time is equal to a negative rate constant times concentration of mercury in the flue gas times the concentration of amended silicates in the flue gas. Now, this radial equation can allow us to test at one condition, at one plant, with one injection rate and obtain a rate constant. And we can use that rate constant and we can say, well, what if I want to inject at this other location, I want to inject at this different rate, and then I'll be able to know what my capture rate would be at that other location, or even a different plant. But in addition to that, and the main purpose for this slide is to show you that when I talk about relative rate or I talk about performance improvement, what I'm talking about is the rate constant obtained for a new product divided by the rate constant we had for the standard product obtained under the same conditions. So at the same plant, same injection rate, same injection location, the difference in the rate constant. Now, as I mentioned, there are many other advantages of amended silicates besides just capturing mercury. Mercury is a non-carbon mineral-based product. It reactively captures both elemental and oxidized mercury, which is pretty unique quality there. It rapidly oxidizes mercury through catalysis. Now, that's not part of the capture step, but that's a fundamental important thing that it does. And we only have to inject a fraction of the amount of material in order to oxidize the mercury as we do to capture. So if you just need to oxidize it so you can capture it in your wet scrubber, you don't need to capture it on the particle, we can inject a much smaller amount and let the scrubber capture the oxidized mercury. That's a catalytic oxidation between the halogen in the flue gas, the chlorine that's already in the flue gas, and the elemental mercury in the flue gas. The amended silicates stabilize metals in the fly ash, all the metals in the fly ash, reducing leaching. The product is not flammable. Amended silicates are not flammable. They're not corrosive. There's no halogens in the product. It doesn't need halogens. Amended silicates preserves fly ash cells. So whatever we have to put in to capture the mercury, you can still sell your fly ash. It has great pozzolanic properties. So you can still sell the fly ash. You can still not have to pay for disposing of your fly ash. It also eliminates the liability of maintaining landfills. Amended silicates improve ESP performance by lowering the mixed resistivity of the fly ash. Amended silicates are compatible with hydrate and trona, and we'll talk about that a little bit more later on. It's tolerant for SO3, and it has about 10 to 15% of the carbon footprint as activated carbon does in the manufacture and use. All right. Now, a number of years ago, 3 years ago, we had up until, still 3 years ago, we had a product that was 2 generations back, I guess. And that product worked well in spray dryer baghouses, and we had some contracts with that product. But that was the only product at that time we had for cold-side ESPs. And this graph represents a test at an actual power plant. And so that top black line doesn't seem to be very good performance. That's how our product worked back then. So that was a product we had up until a little over 2 years ago. Best product we had. And removed mercury in cold-side ESP applications, but not very well. We're not getting to where we need to. 2 years ago, we introduced a product, and its performance is also shown in that curve, a product that is 4 times better in performance than that product. And it's called ASHGX ESP, and we sell that today. It was a product we had up until the end of last year. 4 times improvement, significant improvement, but still not where we need to go, not where we needed to get for cold-side ESPs. So in testing at different plants where activated carbon was also tested and we knew the performance of activated carbon, we then were able to determine, well, where do we need to go with this product in order to have a product that will work in cold-side ESPs in the power plants in the United States. And we determined that we needed a product that was between 5 and 15 times the performance of HGX ESP. And yes, that does mean that it's 20 to 60 times performance of that previous product. So we knew some pathways on how to get there, and so we began making different formulations and different methods of making our product. And we needed a place to test. So we worked with that was really good at determining the relative difference in the mercury capture rate that was representative of coal-fired power plants. And so we worked with the University of Utah to convert one of their facilities to a facility that could test our material. Here we have an Entrained-Flow reactor. Here we have an Entrained-Flow reactor on the left where the reactions take place. On the right, we're showing a feeder, which allows us to have long, consistent, steady feed rate of the material, and that's also important. I'd like to thank Dr. Fry, who managed the laboratory, and Ignacio Preciado, who's the postdoc running the facility, for the work they did for us and continue to do for us. Based on the results of the formulations and the new products that we tested there, we were able to identify best new products to test at a full-scale power plant, and then we took those. We made larger volumes of those new products and tested them at full scale. In December of 2015, we tested at a full-scale power plant, demonstrated this product, prototypes of this product at a full-scale power plant. As shown in this configuration, it's an approximate 100 megawatt boiler, which then comes out into 2 duct trains, each having air heaters, ESPs, ID fans, and then recombining before the stack. DSI trona injection takes place upstream of the air heater for all the time for this plant for HCL compliance. Our mercury emission monitors were located on one train at the inlet of the air heater, the inlet to the ESP, outlet of the ESP, and at the stack. Method 30B samples were taken at each of those same locations for validation, and then on the north duct, we had several more Method 30B sampling to make sure there wasn't a difference in the balance. Now, the pack injection location was right upstream of the ESP. That's where it was, not where we would have put it, ideal for our injection, but that's where the pack injection was, and we used those very same port locations to inject our material, so we had that direct comparison. Pretty short residence time. Oh, I just want to point out before I start, we were very successful at the plant. We did outperform activated carbon at this plant and had to inject much less than the activated carbon. Okay. Now, before we started a test, we did a baseline. That's without our injection. And we started that baseline with the trona off. And with the trona off, for the 70-30 blend of bituminous and PRB, with had a number in carbon of about 5.3%, that was enough to capture the mercury pretty effectively. And so on that baseline without trona, the mercury is well below MATS. But they have to inject trona because they have the HCl permit requirement. When they turned the trona on, the mercury shot up. And that's because the trona scavenged the HCl. The carbon needs the HCl to work well, and so it really diminished the carbon's ability to capture mercury. Now that's unburned carbon, but it has a similar effect on activated carbon. And then for 100% PRB, a similar situation for baseline with no trona. The mercury was actually above, just a little bit above MATS. And then when we turned the trona on, the mercury went up. So in the test actually here, we ran at 100 megawatts. There was 1,500 pounds per hour of trona being injected upstream of the air heater during all our tests. And we injected just upstream of the the ESP in the existing pack ports with very short residence time and non-ideal lance set up for dispersing the product. Here are the results. So that top line there is the product we introduced 2 years ago. So it's the one a little better than the first one. And it worked. It captured mercury, but its performance wasn't that impressive. It wasn't going to get us to where we needed to go. But then we have the 3 prototypes of the new product which we tested, and they all performed very well. All achieved MATS at a reasonable injection rate, and we're talking relative rates of 6, 7.1, and 8 times. Now, in terms of the economics for this plant, we have this divided up into different sections. You know, if the first one is if they don't sell their fly ash, and they use a 70-30 blend, the carbon works better in the 70-30 blend. And so this is just, you have to put in less of our material. And at this plant, they would save a little over $11.5 million a year. If they went to 100% PRB, that means they'd have to put in more carbon and not more amended silicates. Then it would be over $19 million a year that they would save. If they were to sell their fly ash, they get a huge boost in the savings. So if they were to fire on 100% PRB and sell the fly ash, they save over $42 million a year. And the last one's a little bit subtle. Right now they inject trona. One of the reasons why plants inject trona instead of hydrate is because they're worried that the hydrate will impact the performance of their ESP, because the hydrate will increase the resistivity of fly ash and detune the ESP, and if they're also injecting activated carbon tends to not stay in the dust cake, but skip from one field to another, and some of that goes up the stack. That increases the opacity, so they have problems. Now with the amended silicates doesn't skip. It's collected well in the dust cake, so I don't have to worry about that increase of opacity. Plus, it lowers the resistivity of the fly ash cake, which counteracts the impact of the hydrate increasing the resistivity. So that it brings the ESP back into performance. So injecting our material may allow them not to have to worry about that and switch to hydrate, which for them may be cheaper. So and if they did that, that would give them a savings of over $46 million a year. Savings don't include maintenance costs associated with corrosion of adding bromine. They don't include less power input needed to the ESP because our product's helping the ESP performance. They don't include any issues, any savings or concerns about liability of landfill ash or other things like that. All right, now we're going back to that original graph that I showed you. We had that original graph with from a power plant where we tested a product that we had over 3 years ago, and then the one we introduced 2 years ago. Then we had that range, 5 to 15 times we needed to get to. Well, we got to that. We got to the 8 times performance, and that's right in the middle of that range. Now we know actually some pretty small things that we can do to our product to make it a little bit better, and so in a short time we can have a product that's 10 times. And then within a year, we know some other things we can do, a little bit more significant, but fairly straightforward changes we can make to the manufacturing process. We can have a product that's 15 times. At that point, we're going to have a product that's, we already have a product that's competitive in the cold-side ESP market. By that time, we'll have a product that will be competitive at all the plants, coal-fired power plants across the United States. All right, now we also tested this product several months later, that's this year, just a few months ago, in a plant that was configured with a cold-side ESP and a wet FGD. Amended silicates catalytically oxidize the mercury in the flue gas using the HCl inherent in the flue gas from the coal. Again, AS Ultra or any amended silicates, they don't contain halides. The AS Ultra oxidation rate is many times greater than its mercury capture rate. It doesn't add anything to the flue gas or the wet scrubber. It doesn't encourage re-emission of mercury from the scrubber. So Novinda recently performed this test at a power plant configured with a wet FGD at a small rate of the AS Ultra injection. We achieved high mercury oxidation. All the mercury was captured in the ESP. Sorry, all of the AS Ultra was captured in ESP, and the mercury was captured in the scrubber. And here's some more detailed results on that. Okay. All right, so on day one, we started out at about 75 pounds an hour, and we achieved mats. We wanted to get a little bit below that, so we increased to 150 pounds per hour, and we got the mercury down comfortably below mats. And on day two, we continued at the same injection rate, and day three, I thought I had another table. Oh, here's the other table. Okay, so we tested for, also did a week-long test, in which case we ran for approximately 200 hours. And in this case, the average mercury sims were reading below 1 pounds per trillion BTU of mercury. And then the method 30B were a little bit higher, but still well below mats. The average injection rate was less than 120 pounds per hour. And then we also looked at reduced load, because at reduced load, it's you can save money by reducing the injection rate. If you can reduce the mercury during that time, and you have a 30-day rolling average, that can help with that as well. Well, and under the reduced load, under the baseline conditions, we had 1.21 pounds per trillion BTU. And then when we injected the amended silicates, now we're only at 94 pounds per hour. We're at half the mats limit. I want to point out in this, for this power plant, we actually injected through, they have everything set up for activated carbon injection, so we injected the amended silicates through all the activated carbon equipment. It was just, our product was just taken there and injected through the activated carbon equipment. And just getting to the cost now, or the economic benefits. For this particular plant, a lot of times activated carbon needs other additives to perform well. It's poisoned by SO3, so a lot of plants will inject hydrate to remove SO3 so that the activated carbon will work better. That's in some ways counterproductive, because the hydrate will take out some HCl, and that helps carbon, but the SO3 poisons it much more, so they they have to put it in to get rid of the SO3. Obviously, at a lot of plants, they inject calcium bromide on the coal, and that also, is an additive. So at this particular plant, the cost of the BPAC was $576 an hour, $187 per hour, plus the additive total, $763. The AS Ultra cost 300 pounds an hour, didn't need any other additives, so that was the comparison there, 763 to 300. For this plant per year, this plant would pay almost $5.7 million per year for the pack plus additives, and a little over $2.2 million for the Novinda product. And so if they were to use our AS Ultra, they would save almost $3.5 million. Now, I just wanted to go quickly on some of the other slides. I didn't show all the units. On this slide, I wanted to show you all of the units so I give you a perspective of what pounds per million ACF we're talking about. This is another power plant that was particularly challenging for both activated carbon and amended silicates. So challenging that when we tested there several years ago with our product that we introduced several years ago, even though we were only able to achieve MATS compliance at about 16 pounds per million ACF, which is a very high injection rate, it was still, at that time, the best solution they had. Now, if we go back to the plant today, with the product we have now, we can, with the product we can make right now, we can achieve an injection rate of less than 3 pounds per million ACF. Within 6 to 8 months, we'll have a product where we can inject less than 2 pounds per million ACF. And within a year, we'll have a product that's approaching 1 pound per million ACF. Okay. And finally, waiting for lunch. So AS Ultra and amended silicates in general are compatible with DSI injection, including trona or hydrate. So if you need or want to inject those compounds, that's fine. Won't hinder what we do. Our product will still work fine. If you don't want to inject them, our product will work fine. It's either way. We validated the new product mercury capture rates. We've achieved the desired improvements for Cold-Side ESP applications, and we have had corresponding greater oxidation rates for plants configured with a wet FGD. AS Ultra with 6 to 8 times the rate can be supplied now. Within 6 to 8 months, we'll have a product that's 10 times. Within a year, we'll have a product that's 15 times and be competitive at all the coal-fired power plants across the United States. Any questions? No, you're hungry. Where's the food? All right, thank you.